Hello everyone, my name is Dr. Paul Kerstetter, and in this video I'll explain how to and how not to divide a clock in an FPGA. Many designers use simple flip-flop or inverter methods to divide clocks, but did you know this is considered bad practice? And no, Vivado won't even warn you. Clock generation in FPGAs Part 1. Good and bad clock divider design. Sometimes in FPGA design, you need to generate a clock at a different frequency than your input clock. There are several ways to do this. For example, the BUFR primitive can divide a clock down to a lower frequency, while the Clock Wizard IP can both divide and multiply the clock, allowing you to generate frequencies higher than the input clock. However, the slide shows a simple way to divide a clock by 2 using a flip-flop and an inverter. Variations of this approach can use the counters to divide the clock even further. While the schematic may look simple and intuitive, it's actually bad practice to divide clocks this way. Why, you might ask? Because the divided clock is produced by a flip-flop in the fabric rather than by a dedicated clocking resource. That means the generated clock's phase, jitter, and skew depend heavily on regular routing and flip-flop behavior, not on the low skew, low jitter global clock network, BUFG. As a result, the quality and reliability of the clock are significantly worse, and this can lead to timing issues throughout the design. In this slide, I show how the divided clock might be used to register data. Notice that the top flip-flop is clocked by the original input clock, while the lower flip-flop is clocked by the divided by 2 clock. In this slide, you can see the VHDL code used to implement the clock divider and the register flip-flop. The first process, which has the input clock in its sensitivity list, generates the divided clock. The second process, which uses the divided clock in its sensitivity list, shows how the divided clock might be used to capture data. This illustrates how a flip-flop can be clocked by the divided down signal, but again, this is considered bad practice for the reasons discussed earlier. So the question is, will Vivado warn you about this bad practice? The answer is no. Vivado will not generate any DRC or timing errors as long as the resulting clock frequency is low enough. In fact, the timing reports will often look perfectly fine, even though the clocking method is unsafe. Here is an example of a good practice approach for achieving a divide by 2 effect. Technically, this method does not generate a new divided clock at all. Instead, it uses a clock enable signal to select every second edge of the input clock, effectively giving you the same behavior as a divide by 2 clock. This is illustrated in the timing waveforms. Why is this the preferred way to achieve a divide by 2 operation? Because it keeps the design on the global clock network. The global clock network in the FPGA is dramatically better than regular fabric routing and is designed for one purpose, delivering a clock edge to thousands of flip-flops with extremely small timing variation. Some advantages of using the global clock network include ultra-low skew, typically less than 50 picoseconds, high drive strength, allowing it to reliably clock thousands of flip-flops. Dedicated routing resources which isolate the clock from general fabric congestion and reduce variability in clock arrival times. In this slide, you can see the code that generates the clock enable signal. It uses a process with the input clock in the sensitivity list and a simple counter to create the clock enable, essentially a one cycle wide pulse that occurs on every second clock edge. This is how the data is registered. Notice that in this process, the input clock and the clock enable are used, rather than the generated divide by 2 clock from the earlier bad practice example. So how does Vivado know to use the global clock network in one schematic but not in the other? First, Vivado recognizes a signal as a clock because it connects to the clock pin of a flip-flop. It also knows the timing requirements of that clock through a create clock constraint. Finally, the clock typically comes from a clock-capable pin on the FPGA. With these three pieces of information, Vivado inserts the appropriate clock buffer, ensuring the signal uses the global clock network. The buffer may be a BUFG, BUFGCE, or a BUFR. So how do you know whether your design is using the global clock network? One way is to inspect the schematic that Vivado generates. In the slide, you can see the schematic for the divide by 2 clock created with a flip-flop and an inverter, the bad practice version. Inside the red circle is the BUFGCE, which tells us that this signal is being routed on the global clock network. However, the divide by 2 clock coming from the Q output of the flip-flop is not on the global clock network because there is no BUFG, BUFGCE, or BUFR connected to it. This is simply routed through the regular fabric. In this slide, I show the schematic for the single clock with clock-enabled design we discussed in the previous slides. Notice that every flip-flop's clock pin is connected to the input clock. The presence of BUFGCE confirms that the design is leveraging the global clock network. This is considered good practice. Finally, in this slide, I show a screenshot of Vivado highlighting where the schematic tool is located. You need to run synthesis first to access the schematic. Alternatively, you can run implementation and then find the schematic in the left-hand panel under the implementation step. That's all for now. If you enjoyed this video, please like the video and subscribe to the channel. Stay safe, and I'll see you in the next video.